section 8.2, which is called Derivatives of Exponential Functions. So here's what we're going to do. We're going to start by using the definition of derivatives, also known as the difference quotient, to try to compute the derivative of the exponential function f of x equals b to the x. So do you remember this difference quotient? This is it right here. All this is the difference quotient. I'm sure you're having flashbacks to chapter 1 and you're probably feeling a little bit queasy in your stomach. Don't worry, we're not going to use this a lot. In fact, we're just going to use this one time right now. We're going to use this difference quotient, also called the definition of a derivative, to figure out what the derivative is of this, f of x equals b to the x. So let's do that now. What this says is that the derivative is equal to this highlighted bit, so it's the limit as h approaches 0 of f to the x plus h. So what does that mean? That means wherever I see x right here, I should put x plus h. So I would have b to the x plus h minus f of x. Well, f of x is just b of x. So then I'm going to put b to the x power here. And that's all over h. Okay, let's go another step. What we can do with this first term here, b to the x plus h. Well, remember, you can add exponents when you're multiplying powers with the same base. So I know this is kind of going backwards from that, but I could take this b to the x plus h and write it as b to the x times b to the h. Does that make sense? I'll say it again. If you had the same base like you do here and you're multiplying, you could add the exponents together and get x plus h. So I've just kind of gone backwards from the normal way we do that. Minus the same thing, b to the x power all over h. What was the purpose of that? Well, now we have a greatest common factor we can factor out of both terms. So we have the limit as h approaches 0, factor out a b to the x power, you'll be left with b to the h, b to the h minus 1 all over h. And here's the last thing. This b to the x power, that has nothing to do with h, right? The limit is as h approaches 0. Well, b to the x has nothing to do with h. It's a constant. So what we can do is just move that b to the x out front. So you'd have b to the x power times the limit as h approaches 0 of b to the h minus 1 all over h. I'm going to write in here that the reason this moved up front, in case you wonder about this later, is because it does not depend on h. So that's the reason we could move that out front. Okay, so now what we're going to do is we're going to focus in on this bit right here. And specifically, we're going to, ask what happens as this limit approaches 0. So we're going to do this for different bases. We're going to do it for two different bases. We're going to try it when b is equal to 2. And we're going to try it when our b is equal to 3. And you'll see why we're going to try these specific two in just a second. So I'm not going to actually show you this in the calculator. I think it's a little bit pointless. But basically, if I took an h value that's very close to 0, right? That's what we're doing. We're approaching 0. So why don't we start with 0.1? If I put 0.1 in here, I'd have 2 to the 0.1, get that answer, take away 1, and then divide all that by 0.1. And if you do that, you're going to get 0.7177. Again, I don't think there's any point in me showing you this in a calculator. So then what I do is do the same thing, but I'll get even closer to 0. I'll put 0.01 in there. 2 to the 0.01, take away 1 over 0.01. And if you do that, you get 0.6956. Let's get even closer to 1. 0.001. What's 1/1000th from 0? It's very close. If you put that into this statement right here, you'll end up with 0.6934. Let's get even closer to 0. Let's put 0.0001. What's that? 1/10,000th away or something? And if you do that, you're going to get 0.6932. So if we round to 3 decimal places, it looks like as we're approaching 0 here, we're getting very, very close to 0.693. I'm just going to put this arrow here to show we're approaching 0.693. Okay, not really of any interest or what's the point of this, but just trust me here. Let's go on. Let's do the same thing over again, but this time we're going to use a base of 3. Our b is 3 in this time. So again, we're going to take ever closer values to 0 here. So we'll start with 0.1. 3 to the 0.1, Take away 1, divide all that by 0.1, you'll get 1.1612. Try it again, but put 0.01 into the h's. You'll get 1.1047. Try it again, but put 0.001 into here. You'll get 1.0992. Try again with 0.0001 into those h's. You're going to get 1.0987. And again, as we approach 0, what seems to be happening if we round to 3 decimal places is it's approaching 1.099. Okay, why did I do this? Why did I take one with a base of 2 and one with a base of 3? Well, the key to this is, when we did it with a base of 2, it seems to approach 0.693, which is obviously lower than 1. When I used a base of 3, it seems to approach a number 1.099, which is above 1. So it might lead us to speculate that there must be a b value between 2 and 3, that if we put it, in this statement right here, that we would end up, as it approaches 0, that the limit would approach 1. And that could be very, very useful. So what this means is, if we were taking the derivative of 2 to the x, and let's just look back here again, we said when we take the derivative of b to the x, you end up with the same thing, b to the x, times this limit part right here. So in this case, if I was taking the derivative of 2 to the x, what I would have is 2 to the x, and then that would be multiplied by 0.693, because that's how much we found this highlighted bit. I suppose with the highlight I should include the limit too. We found that the limit is equal to 0.693, so we would have 2 to the x times 0.693. With the base of 3, if we were taking the derivative of 3 to the x, we would again have as our derivative 3 to the x, just like we saw up here. You end up with b to the x sitting out front, and that would be multiplied by the limit amount. And we found the limit amount was 1.099. So what we're looking at here is, wouldn't it be great if we could get this part in brackets to be 1? Wow, we'd have a very, very simple derivative, wouldn't we? And that's what this last column's for. It's for my students to kind of guess what would be the amount for our base to be in order to get the limit to be 1. And obviously it has to be a value between 2 and 3. So I asked my students, guess what will approach 1? It must be a b value between 2 and 3. And as you can see, when it was a base of 2, it was quite a ways from 1, wasn't it? It was way down at 0.693. But when it was a base value of 3, it was just a little above 1. It was 1.099. And for that reason, most students figure out that it should be something closer to 3 than 2, so more than 2.5. Some kids tried 2.6, 2.7, maybe 2.75, and we take a look at all those things, and then we actually find that there is a base that works. There's a number b for which the limit is 1. We call this number e, Euler's number, and this number is approximately 2.71828 ... goes on and on and on. It's an irrational number, kind of like pi. So what I'm saying here is this highlighted bit up here, if you put e into the b, in other words, if you have the limit of e to the h minus 1 over h as h approaches 0, the answer will be 1. Therefore, if f of x equals e to the x, then f prime of x, the derivative of the function, equals e to the x. Exactly the same thing. Or another way you could write that is the derivative of e to the x equals e to the x. This is the easiest derivative of all time. It ends up that the derivative of the function equals the function itself. Now this should say e right here. The exponential function f of x equals e to the x. I'm going to say something about it in just a second, but first of all, let's just sketch it. We did this sort of things last time. If we have a base of e and we raise it to the 0 power, it's 1. That's always going to be the case, that it goes to the 0.01, right? And remember, it got higher and higher and higher here, and it got closer and closer to the x-axis here. So it kind of goes like this. At the point 1, how high would it be? Well, e to the 1 equals e. So it'd be somewhere around 2.7. So I'll put it right around there. So this would come up something like that. There's my graph for f of x equals e to the x. Now, the cool thing is, with the exponential function f of x equals e to the x, this function is its own derivative. So for example, if I was to draw the tangent line at this point right here, if I draw the tangent line, looks something like this, you know what the slope of that would be? It would be e to the 0, or 1. If I was to draw another tangent line right at this point, right, something like this, what would the slope of that one be? Well, that was when we had x value of 1, so the slope would be e to the 1, which is just e, or 2.71, whatever. So whichever point you take on this e to the x graph, the tangent line, the slope of the tangent line at that point will be exactly equal to the y value of the function itself. Pretty crazy. So just to summarize, it has a tangent line with a slope equal to the y coordinate of the point. Okay, so let's try differentiating a few things here. The first one we have is x squared times e to the x. So we have two different pieces here. Which rule are we going to have to use? This is the product rule. So for the product rule, the way I like to do it is I first of all take the derivative of the first piece. The derivative of x squared is 2x, and I multiply it by the second piece, e to the x, plus the first piece, x squared, times the derivative of the second piece. Well, the derivative of e to the x equals e to the x. You gotta love it. And then the only other thing you could do here, which is a good thing to do, is to factor out a greatest common factor. So I see an x in each one of these things, and I see an e to the x in each one. That leaves us with 2 in the first term and x in the second term. If you really want to, do more steps, you just love writing mathematical statements, you could probably write the bracketed part as x plus 2, but it's certainly not necessary. Okay, this one, e to the sine x. Which rule are you going to use here? This is going to be the chain rule. The outer function is e to the something, and the inner function is sine x. So let's start with the outer function. We said the outer function is e to the something, and remember the derivative of e to the something is e to the something. So we're still going to have e to the sine x times the derivative of the inner function. The inner function is sine x, and the derivative of sine x is cosine x. So that's it. You could just stop right there. Okay, the last one here, a little tricky. You're going to have product rule and chain rule, I believe. So we've got one piece here and we've got one piece here. We're going to use the product rule. So the first thing we're going to do is take the derivative of the first piece, and you got chain rule here. So first we have to take the outer function, which is e to the something. The derivative of e to the something is e to that same something. But then we need to multiply by the derivative of the inner function, which is negative 3x. And the derivative of negative 3x is negative 3. Okay, then we multiply that by the second piece, which is cosine 2x, plus the first piece, which is e to the negative 3x, times the derivative of the second piece. So again here we have a chain rule situation. The outer function is cosine of something, the inner function is 2x. So we're going to start with the outer function, cosine of something. The derivative of cosine is negative sine of the same thing, 2x. And then we've got to multiply that by the derivative of the inner function, and the derivative of 2x is 2. Squeezing it in here. So a little bit to clean up here. Let's see, in the first piece we have this negative 3, and then e to the negative 3x cosine 2x. So I think that's about all we can do there, is just move the negative 3 out front. E to the negative 3x cosine to the 2x. Now we have a negative sign here, so our next piece is going to be minus. We've got 2 e to the negative 3x and then sine to the 2x. Now I think we can take out a greatest common factor. There's negatives in both, so let's take out a negative. There's e to the negative 3x in both. And what that leaves us with is 3 cosine 2x minus 2 sine 2x. Sorry, I made a mistake. Plus, right? This was negative. Negative times this is negative. Negative times a positive is a negative. Sorry about that. And that is your answer. Okay, last question. We're going to sketch the graph. Oh no, sketch the graph. Do we really have to? Yes, we have to. Let's do it. We're going to do this pretty fast though. So the graph is y equals e to the negative x squared. The domain. What number could go into this x? anything can go into this. So x is an element of all reals. The intercepts. Well, to get the y-intercept, you put 0 into the x. So your y-intercept, you would have y equals e to the negative 0 squared. 0 squared is 0, negative 0 is still 0, so you get e to the 0, and e to the 0 is 1. So one of your intercepts is at 0, 1. And for the x-intercept, you're going to put 0 into the y. So you get 0 equals e to the negative x squared. Is there anything you can raise e to and get a value of 0? No. If you think of the graph right here, this blue graph here never hits the x-axis. Remember, we always had an asymptote at the x-axis. So you're never going to get a y value of 0. It's not possible. So your only intercept is this 0, 1. And I guess we could write none here for the x-intercept. Okay, symmetry. If we put negative x in there and square it, and then we simplify that, we're going to get e to the negative x squared, negative x all squared, is x squared. Hey, we're back to where we started. So what's that mean? It means we have even symmetry, right? It's going to be symmetry about the y-axis, reflection over the y-axis. Asymptotes. Vertical. You only get vertical asymptotes when there's a fraction, so vertical we would say none. For horizontal, we want to see what happens is we take the limit of our function as x approaches positive and negative infinity. And whether you put positive or negative in here, when you square it, you're now going to have positive infinity. Then you're going to make it negative. It's going to be negative infinity. So you're going to have e to the negative infinity, basically. Well, this is a flipping negative, so it's going to be 1 over e to the infinity. That's 1 over some massive number. When you have 1 over a massive number, what do you get? You get 0. So what that means is your horizontal asymptote is at y equals 0. Intervals of increase or decrease. Okay, it's time to take the derivative. Y prime. Alright, this is just a chain rule. So we have e to the something, so we're going to start by taking the derivative of that. That would still be e to the something, that same something. And then you got to multiply that by the derivative of the inner function, which is negative x squared, and that equals negative 2x. So you end up with negative 2x e to the negative x squared for your derivative. And what we want to find is, what are the critical numbers? So to do that, we're going to set this negative 2x e to the negative x squared, we're going to set it equal to 0. And it turns out either negative 2x could equal 0, or e to the negative x squared could equal 0. When would this equal 0? When x equals 0. When would this equal 0? Never. We talked about that right up here, right? This is exactly the same situation. It never happens. So we only have one critical number, which is 0. So now what we can do is put those on our wiggle graph, put 0 here. We're going to try this out. Where are we going to try it? Right here. If I put 10 in there, well, remember, this piece here is always going to be a positive y value. Think again of the graph. You're always going to have this asymptote right here, so it's always going to be positive. But in fact, we already figured this out anyway. We figured it out over here. And if we just followed along right to here, 1 over e to the infinity, yes, it approaches 0, but it approaches it from the right-hand side. So this is a positive amount. So this is positive. And then negative 2 times 10 is negative 20, so this is negative. Negative times positive is negative. So this is negative, which means it's decreasing here. If you put a negative in here, well, even if you put a negative in this piece, you still square it, you get the same amount. So this is positive, and a negative times a negative here equals a positive. So this is increasing. Increasing and then decreasing? That means we have a maximum right there. So let's summarize. The areas of increase are from negative infinity up to 0, and the areas of decrease are from 0 to infinity. And then our maximum is when we get 0, and the point's going to be 0. I think we already found this point, didn't we? 0, 1 is our point. So our maximum is at 0, 1. Okay, concavity. Got to get the second derivative. So looking at this blue square here, we've got to get the derivative of that. Product rule this time. So we have y double prime equals the derivative of negative 2x is negative 2, and multiply that by the second piece, which is e to the negative x squared, plus the first piece, which is negative 2x, times the derivative of the second piece. Well, wait a minute, isn't that exactly what we started with, e to the negative x squared? e to the negative x squared? Yeah, so this piece, the derivative, must be the whole boxed part. If you don't believe me, you can do the whole thing again, but you're going to get negative 2x e to the negative x squared, right? Because you would take the derivative of this, which is e to the negative x squared, and then multiply by the derivative of this, which is negative 2x, and that's how that works. Okay, so we have negative 2 e to the negative x squared. Negative and negative is positive, so we have plus 2x and 2x is 4x squared, and then e to the negative x squared. We could factor out a negative 2 e to the negative x squared, and we'd be left with 1 minus 2x squared. And now what we're going to do is we're going to find our pips, our potential inflection points. So this whole bit here has to be equal to 0. Either this first bit, the negative 2 e to the negative x squared equals 0, or the second bit, 1 minus 2x squared equals 0. Well, if you look at this bit, you're going to divide both sides by 2. You're going to have e to the negative x squared equals 0. But this is exactly what we've talked about a couple times now. You can't make that equal 0. It's impossible. So nothing's coming out of there. Solving this one, let's move the 2x squared over, divide by 2, and then take the square root of both sides, remembering that we have to do plus minus. So x equals plus or minus the square root of 1 over 2, which is the same as, well, the square root of 1 is just 1, so plus or minus 1 over root 2. And man, we ever out of room here, but we're going to put on our wiggle graph those 2 points, 1 over root 2 and negative 1 over root 2. And I suppose in order to do this, I need to know approximately how much that is. It's approximately 0.71. So in between here, easy, we're going to use 0, and we can plug it in to this right here. 0 squared is 0, negative 0 is still 0, e to the 0 is 1, negative 2 times 1 is negative. And if I put 0 in here, I get 0 times 2 is 0, so 1 minus 0 is 1. So I have a negative times 1, or a positive. Negative times positive is negative. So we got negative here, which means it's concave down. Let's try something bigger than 0.71. How about 1? If I put 1 in here, I get 1 squared is 1. E to the negative 1 is 1 over e, that's a positive amount, and a negative times a positive is a negative. So this whole first part is negative. If I put 1 in here, I get 1 squared, which is 1, times 2 is 2. 1 minus 2 is negative 1, so it's negative. Negative times a negative is positive. So up here it's positive or concave up. If I put negative 1 in here, it's going to be exactly the same. Both our x's are squared, which will turn them positive. It's going to be exactly the same as this, which is what you would expect because we already said up here that the symmetry is even, so we'd expect it to be the same. So this is going to be plus or concave up as well. So we've got concave up from negative infinity to negative 1 over root 2, as well as from 1 over root 2 to infinity. And it's concave down from negative 1 over root 2 up to 1 over root 2. We have absolutely nowhere to do any of this work. It's really kind of a mess. Last thing, points of inflection. Wouldn't you know it, we have 2 possibles because we got the concave up, concave down. We got the concave down, concave up. So our points of inflection are at negative 1 over root 2 as well as 1 over root 2, and we need to find those y values. So to do that, we got to go all the way back up to the top. And it doesn't matter if we put the negative or the positive one in because they're both going to be positive when you square it. So I have e over negative, our value is 1 over root 2, and then we're going to square that. Well, that's e over negative 1 over root 2 squared is 2. This is a flipping negative, so you get 1 over e to the 1/2, and 1/2 means square root. So you get 1 over root e in both cases here. And 1 over root e, and we better write in approximately how much that is. 1 over root e is approximately 0.61. Okay, we're ready at last to graph this thing. So I think, yeah, our maximum point was at 0, 1. So let's make this 1 right here. And then we had an asymptote at the y equals 0 line. So this is, I think, as low as it's going to go, and it's not going to get there. And then our other points, Remember that this amount here was 0.71, so let's make our other points 1 here and -1 here. So if I'm going to put the point 0.71, 0.61, that would be somewhere, I don't know, around there. And -0.71 and 0.61 would be somewhere around here. And don't forget to put I forgot to put our point right here. Okay, now remember, it's getting closer and closer to this asymptote, and it's getting closer and closer to the asymptote here. It should be increasing up until 0. It should be concave up until our inflection point, and then concave down. Now if I do it perfectly, it'll look like a mirror image of this side, but of course I won't do it perfectly because I can't do it perfectly. It should be decreasing now for the rest. It should be concave down here, and then it should be concave up there, and that is what our drawing looks like. We've done it. Sorry about this big mess here, but I'm hoping you follow the steps.